Okay, now we're going to talk about the second derivative test. Now this test, even though I know we've been associating second derivative with concavity, this test is only used to determine extrema. It uses the concept of concavity, even though you may not realize it, but it's used to find relative maximum and relative minimum. So it's just another test. So the first derivative test can be used, but the second derivative test in a lot of cases can also be used. So first of all, let me try to explain it. If a graph is concave up at a critical number, then the function must have a relative minimum at a critical number. Because see, if you've got a critical number, if this is a critical number and the graph goes through it when it's concave up, as it goes through it, then you've got to get a minimum there. There's no other option. And then likewise, if the graph goes through there concave down, you've got to get a maximum at that critical number. So basically, that's the geometry behind it. So here's the formal second derivative test. Let's say that the first derivative of c is 0. Now that just means that c is a critical number for the function. And let's say the second derivative exists on some open interval that contains c. Now, if the second derivative is positive, and this is where it gets a little crazy, when the second derivative is positive, f of c is a relative minimum. Now, why would that be the case? Well, it goes back to what I just said. If this is a critical number, if the second derivative is positive, then you have concave up. And if you have concave upward at that critical number, then you can only have a minimum there. You can't have a maximum, you have to have a minimum. Okay, now if the second derivative is negative at the critical number, then you've got a maximum. So again, if this was a critical number, if the second derivative is negative, that means you're concave down. Well, if you're going through that value concave down, that means you've got to have a maximum. Okay? So, and then the second derivative might fail. So if the second derivative is 0 at a critical number, then you're not going to know what's going to happen. You might have a relative min, you might have a relative max, or you may have neither. So you have to actually revert back to the first derivative test. All right. You can read this. You can read this little paragraph on your own, freeze the video and read it for you. I've already explained some of that for you. But let's go ahead and get on to the second derivative test. Okay, so basically, you're actually going to use all three of these functions in this test. You're going to use the function y, you're going to use the first derivative y prime, and you're going to use the second derivative y double prime. Okay, all right, so here's what we're going to do. We're going to use the first derivative to get our critical number. So set your first derivative equal to 0, solve it for your critical number just like we were taught before. So the critical number is x equal 1. Now, we're going to need the second derivative. Why do we need the second derivative? Because we're going to plug this critical number into the second derivative. So let's take this critical number 1 and let's plug it into the second derivative. So the second derivative evaluated at 1 equals what? Let's see, 24 times 1 squared is 24. Now, is that going to be, is 24 positive or negative? Well, obviously 24 is positive. Okay, well what does it say if the second derivative is positive at a critical number? Well, that would be number 1. If the second derivative is positive at a critical number, then f of that number is a relative minimum. So f of 1 would be a relative minimum. So now, where does the original function come in? The original function comes in because to get the actual minimum, you have to plug 1 back into the function to actually get the minimum. So if you plug 1 back into this function, you'll get -3. So -3 is a relative minimum for that function. Okay? So it's not difficult to do, you just have to follow the steps. So here's a function. Get the first derivative so you can get the critical numbers. Now, the first derivative, if you set it equal to 0, you'll get 3 critical numbers. 0, square root of 3 minus square root of 3. We did this earlier. Okay, now you need the second derivative. Okay, so that we can do the test. So we have the second derivative is 12x squared minus 12. Then we're going to plug each of these into the second derivative. Plug 0 in to the second derivative, and I get 12 times 0 minus 12. That's negative. So that means f of 0 is a relative max. Now plug square root of 3 in. So evaluate the second derivative at square root of 3. Well, that's going to be 12 times square root of 3 squared, which is 36, minus 12 is 24. So that's positive. So f of square root of 3 is a relative minimum. And then plug negative square root of 3 in, and you're also going to get a positive. So f of negative square root of 3 is a relative minimum. And now to actually figure out what f of 0, f of square root of 3, and f of negative square root of 3, that's where you go back to the original function and plug them in. So if you plug 0 into this and solve it, you get the y value of 0. If you plug plus or minus square root of 3 into this, it's going to give you the same number, -9. So we get a relative minimum of -9 at square root of 3. We get a relative minimum of -9 at minus square root of 3. And we get a relative maximum of 0 at x equals 0. Okay, now the second derivative test actually works very nice on polynomials. You really want to stay away from it unless you're forced to use it by, say, some mean professor on other functions. The reason is, here's a quotient, 4 over the square root of x squared plus 1. Well, the first derivative I can get using the quotient rule. But then to get the second derivative, it's even more difficult. So that's why you want to use this test on functions where it's functions that are easy to differentiate. And polynomials are usually easy to differentiate. So that's why I said polynomials. But anyway, from the first derivative, you can see that the critical number is 0. Now go to the second derivative and plug 0 into it to see if we get a negative or positive. Well, if I plug 0 into the second derivative, I'm going to get 8 times minus 1, so I'm going to get -8 on top, and the bottom is going to be 1 cubed, so I'm going to get -8. So the second derivative is -8, and that's less than 0. Well, since the second derivative is negative at 0, then I know f of 0 gives us a relative max. And to figure out what that relative max is, I just need to put 0 into this function and evaluate this function at 0 to get 4. So 4 is the relative max. Okay, I'll finish this. Well, before I get into this any further, let me just tell you, I didn't do an example where the second derivative test failed. But again, let's say that for some reason the second derivative test failed, then you would have to you'd have to go back to the first derivative test. So how about this? If you had y equal x cubed, okay? All right. The first derivative would be 3x squared. Okay? Now, that would equal 0 when x is 0. Okay? So that would be your critical number. Well, then the second derivative would be 6x, right? Okay? Well, but if you evaluate the second derivative at this critical number, you're not going to get a positive or negative value. You're going to get 0. So what that means is you have to go back to the first derivative test. So what would I do? Well, I would go back to the first derivative test. I'd say, okay, using the first derivative test, I'd break the number line at 0, the critical number, and then I would pick a number to the left of 0 and a number to the right of 0, and then I would evaluate the first derivative at that number. Okay, well, if I evaluate the first derivative, which is 3x squared, if I evaluate 3x squared at -1, that's going to be a positive number. So the first derivative is positive at -1. But if I evaluate the first derivative at 1, I'm also going to get a positive number. Okay, well, notice that there's no change as we cross 0. The second derivative is positive on both sides of 0. So for the first derivative test, I know that 0 does not give me an extreme value. Okay, so let's end this section with an application. This says find the point of diminishing returns for the model below. R is revenue in thousands of dollars, and X is the advertising costs in thousands of dollars. Now, the point of diminishing returns is actually the point of inflection. So let me explain that in just a minute. You might have a function that's increasing, and it's continued to increase, but at some point, the rate at which it's increasing, maybe right here, begins to slow down. So it's still increasing, but it's increasing at a slower rate. So in other words, it's changing from concave up to concave down. And so there, that point would be the point of diminishing returns. So I've got a revenue function here, 1 over 20,000 times this polynomial. Okay, so I'll let you find the derivative. If you can differentiate this, and I want you to find the derivative and show that the first derivative is -3 over 20,000 times x squared minus 300x. Well, remember, I'm looking for this point of diminishing return, so I need the second derivative. So I'm going to find the second derivative here, and I get -3 over 10,000 times x minus 150. Now, this is the second derivative. So this point of diminishing return will happen when the second derivative is 0. Okay? So I set this equal to 0, and you can see that the only way this can equal 0 is if x is 150. So x equals 150. Now, technically, you still need to check on each side of 150 to make sure that the concavity is changing, but I can actually do that visually, because if I plug, say, 149 in, I'm going to get -1, so I have a negative times a negative, so I'm going to get a positive, so the graph's concave up to the left of that point. And then if I plug 151 in, I'm going to get negative times a positive, so it's concave down to the right of that point. So based on that information, I do know that the concavity changes when x is 150. So the point of diminishing returns occurs when x is $150,000. And I guess if you wanted the revenue that went with that, you could plug the $150,000 back in up here if you needed it. Okay, so that pretty much ends the section on the concavity and the second derivative test, and we'll get into some other applications of derivatives next.